Hello everyone, it's my pleasure to be in the RSG conference and talk about our works on the Preterm birth dream challenges. And my name is Zhoujingpeng. You can call me Wallance. I'm the second year PhD student in the Department of Biostatistics and Medical Informatics in University of Wisconsin-Madison. Other team members are Jifan Gao, who is the third year PhD student, and Dr. Wanhua Chen and Dr. Zheng Tang are the associate professor in my department. So my topic today is the Ensemble model to predict the preterm birth using the vaginal microbiome data. For the introduction part, the preterm birth dream challenge has two tasks. The task one is the prediction for the preterm birth, which use the vaginal microbiome data that's collected from pregnant women. So the definition of the preterm is defined as the birth prior to 37 weeks of gestation, which collect from the pregnant women. The task two is the prediction of the early preterm birth, which is defined as the birth prior to 32 weeks of gestation. So our team mainly focuses on the task one. Since each subject may have multiple specimens, the training data set contains 3,578 specimens from 1,268 subjects across 10 different projects, of which 416 subjects are delivered preterm. So the testing data set is unseen by the challenge participant, which includes the specimen that collect no later than 32 weeks. So the data is provided by the preterm birth challenge organizer, and the data we used includes the assigned sequence variant, which is the relative abundant data in the species, genus, and family levels, and also phenotype rates data with phylogenetics distance 1 and 0.5. We also use the metadata that include age, collected weight, and the racial category, and also community state type data and 7 different alpha diversity metrics, such as Shannon diversity and inverse Simpson. So this is the workflow for our models. We firstly remove the lower abundant taxa, which have less than 5 non-zero observation in any projects. After that, we just apply the central log ratio transformation on the taxonomy data and the phenotype type data, so which is the commonly used normalization measures on the microbiome data. So here we built 2 prediction models. The prediction model 1 is called all data model, which is use all the specimens in these 10 different projects. We found project G has different preterm birth associated taxa compared with other projects. So we built another model 2, which is unique to project G and use the specimen only in project G. So we get our final models by Ensemble, the model 1 and the model 2. Next, I will go to the detail for each step. So firstly, we just apply the filter to this original data, because the original taxa have some large amount of taxa, but most of them may not have enough observation in most of the projects. After this filtering, the retained taxa has average proportions range between 95% and 82%. It shows the retained taxa do not lose much information after this filtering. So in this step, we have filtered out almost 6,500 taxa and include 2,580 taxa in our prediction models. So the taxonomy data and the phenotype data are relative abundant data. We need to apply some normalization measures before we put them in our models. So we applied the central log ratio transformation on each project's data. For each observation of the taxa in each specimen, we divide the observations by the submission of the observation of taxa in each specimen and take the log. So after that, we can map the composition data, which is relative bound data, to the Euclidean space. Here we use the normalized data to build our two models. First, we can see that project G has very different sequence depths than other projects. The average sequence depth of the project G is almost 10 times than the project I, which has a second higher average sequence depth among all the projects. We also do the project-to-project testing and training metrics. The column is the testing project's ID, and the row is the training project IDs. We can see the model that trained only by project G has good performance in the testing projects in itself, but have bad performance on other testing projects. So it shows the project G has different preterm birth associated taxa compared with other taxa. So except the model 1, which built by using all the specimens, we also built another model 2, which is trained by only project G, and treated is complementary to model 1. So for model training, we use the 19 GBM to train the model, which has high performance in the machine learning computation. And the tuning hyperparameters is tuned by 5-fold cross-validation on the subject's levels. So the subject's levels prediction is weighted by the customized weight of a specimen level prediction, which I will talk in the next slides. The hyperparameter tunings was automatically done by Optuna package, and we stop the tuning part when the AURC achieved the highest on the training data set. So here we can apply our training model on the testing data set and get the specimen level predictions. So here we use the customized weight to combine the specimen level prediction to obtain the subject level prediction. So intuitively, the more recent specimen collected is more representative to this subject. So we just weight the specimen levels prediction by the collected weight. So the weight is for each specimen, the collected weight divided by the submission of the collected weights of all the specimens in this subject. So for example, if we have subject A, which has 3 different specimens with collected weight 16, 24, and 30, their weight on the specimen level should be 16 divided by 70 and 24 divided by 70 and 13 divided by 70. So now for every specimen in for every subject in testing data set, we can get the weighted prediction from the specimen level prediction. The final step is that how we assemble the prediction of model 1 and the prediction of model 2. So for each project, for each subject from different projects, the weight for the model 1 prediction is different, and for model 2 prediction is different from the projects from the subject from different projects. So for example, for every this plot shows the weight for the model 2. That's the subject come from a different project. For example, you can see we give the weight of the model 1 and model 2 in project A, so almost 0.5 here. And for the weight for the subject from the project G is almost 0.65 over here. So here we need this weight is generated by the logistic regressions with collected weight and the sequence depths as the features. So we need to wait for each subject in the testing data set. We need to find out how similar this subject is come from each project in terms of the collected weight and the sequence depths. For example, if a subject in the testing data set is more similar to the subjects from the project A, we would assign the weight of the model 1 and model 2 is almost equal to 0.5, but it's more similar to project G. We would assign the weight for model 2 is 0.65, which is higher than the weight of the model 1. So now we can get the different customized weight for the model 1 and model 2 for each subject in testing data set, and we can get an ensemble model prediction. So here is the result for the task 1 and the task 2. So we have in task 1, the AUROC is almost 0.68 and the AUPR is almost 0.57. In task 2, we have AUROC almost 0.66 and AUPR 0.50. So this model can be widely applied to predict other disease or phenotypes. So if you are interested in our model and want to try it on your own data, you can please feel free to contact us. So here we team many thanks to the challenge organizer for hosting this great event, and thanks to the participant cohort for contributing the data. So our team is funded by the NIH and the NSF. So thank you for listening. I'm happy to take any question you may have.
Just so you know, everybody talking, the only way that the people online can hear is if the questions are repeated. So I'm just going to ask the speaker to repeat the question before you answer it. Okay?
Sure.
First of all, thank you so much for your work. I was curious, as I shared earlier, in UWiscMadison and her team's work, they found that there was a greater diversity in the vaginal microbiome earlier on in pregnancy. And in your work, you had used collection weight as a feature where it seems though samples collected later would be have greater weight.
Yeah.
I wonder, have your team tried it where maybe inverse, where it would be the earlier samples that would have greater weight, and see how that might affect your model performance?
Okay, so this lady's question is that why we use the give the heavy weight on the samples which collect later. She wondering whether we can use the give the weight to the first collect the samples. This is a great question. Actually, we have tried a different weight for the collection weight, such as equal weight or give the weight to the early collect sample. But however, due to the according to our model's performance, give the weight to the later collect the specimen, will have better performance in our AURC. So it's a roughly weight for the models. So just a technical part. Thank you.